Okay, hi. In this video, I'm going to show you how to solve another application of differentiation. In this case, it says liquid is poured into a container at a rate of k cubic meters per second. The volume of liquid in the container is V cubic meters, where V is equal to 1/3 pi h squared times the quantity 3k minus h, and h is the depth of the liquid in the container. What we want to do is to find, in terms of K, the rate at which the depth changes when h is equal to 2k over 5 meters. Before we continue solving this problem, it is important that you know that whenever we speak of rate of change, in calculus that means it's the derivative. So for example, if I say the rate of change in the volume is given by a certain amount, then rate of change of V means dV over dt, and it's always with respect to time. Okay, so this is rate of change of the volume, and whenever I say the rate of change of the height or the depth, in this case h is the depth, so dh over dt is the rate of change of the depth of the liquid. Okay, so basically that's the idea that you need here. Now let's picture what is happening in the problem. So we have a container. Let's just pick a random container. Let's have an irregular container. So what is happening is you're pouring some liquid inside the container, and when you do that, then there will be an accumulation of liquid inside the container, and as you continue to pour the liquid in the container, then the volume increases, or the volume of the liquid inside the container increases. So what we want to find here is how fast, so the rate, how fast is the height increases when you pour the liquid in the container at the rate of k cubic meters per second. So you're putting some liquid inside the container, so definitely the volume inside the container will increase, as well as the height of the liquid in the container. But take note that the rate at which the volume is changing is not the same as the rate of change of the height. Okay? Now, so if it says that the liquid is poured in the container at the rate of k cubic meters per second, so the rate of putting the water inside, or the liquid inside the container, is k. That means the volume inside the container is also changing at the rate of k, right? So we could say, or we can say, that the change in volume with respect to time inside the container is just equivalent to the rate of change at which you pour the liquid inside the container. So dV over dt is also k. Okay, so let me say that again. Where you're pouring some liquid inside the container at the rate of k, that means the volume will also have a rate of change as k. Now, so what we want to find is the rate of change at which the depth is changing. So we want to find dH over dt, considering that h is equal to 2k over 5. Now, so how are we going to continue with the solution? As you can see, the volume has the equation 1/3 pi h squared times 3k minus h. And if you recall our previous examples in the class, whenever we take the derivative of this with respect to time, then you have to differentiate also h and k with respect to time. Since this is a more complicated problem, it is needed, or it is necessary to simplify or to express the right side of the equation in terms of one variable only. So it's either we change h into k or we change k into h. But since we want the derivative of h with respect to time, you cannot take away the h. You have to retain the h. Otherwise, once you differentiate, you will not get any dh over dt. Okay, so if h is 2k over 5, then I can manipulate this equation to come up with a k that will replace the k in the volume equation. To do that, so if I have h is equal to 2k over 5, this simply means 5h is equal to 2k. And if I divide this by 2, then k is 5h over 2. And that means v is equivalent to 1/3 pi h squared, 3, but k is known to be 5h over 2 minus h. And then we continue to simplify the volume function. So v now is equal to 1/3 pi h squared times 15h over 2 minus h. Now you can combine 15h over 2 and h, or subtract this and make this in a single expression. Take note that h, or minus h, is equivalent to minus 2 over 2h. And if I simplify this further, so v now is 1/3 pi h squared times 15h over 2 minus 2h over 2 will become 13 over 2h. And finally, so v is equal to, so you have 1/3 times 13 over 2, that's 13 over 6 with a pi. H squared times h will be h cubed. So now we know the volume equation in terms of h. So you have v is 13 over 6 pi h cubed. Okay, again, what we want to find is dh over dt, the rate at which the depth changes. Okay, so this is still unknown. Now, since we have v in terms of h, if we differentiate this function, so dv with respect to time. So again, this is with respect to time, not with respect to h. So by the power rule, so you multiply 13 over 6 pi by 3. So let me write that down. So 13 over 6 pi, so times 3, so it's like bringing down the 3, then h squared times dh over dt, same as implicit differentiation. And if you further simplify it, this will become 13 over 2 pi h squared dh over dt. Now remember, at the start of the solution, we said dv over dt is equal to the k. The rate at which the volume is changing is equivalent to the rate at which the liquid is being poured inside the container. So this dv over dt can now be replaced by k, then equals 13 over 2 pi. Now h is 2k over 5, so 2k over 5, so h squared times dh over dt. And this is what we want to find. So that means we have to take away all the other expressions connected to dh over dt. And that can be done by simply dividing this, or both sides, by 13 over 2 pi times 2k over 5 squared. And that will cancel these numbers or expression. So on the other side, you should also have 13 over 2 pi times 2k over 5 squared. So this will cancel and this will cancel. So basically this is your dH over dt. So what is left is to simplify this so that you have a single fraction. Okay, so we have dH over dt is k over 13 over 2 pi times 2k over 5 squared. If I simplify this is equivalent to 13 over pi over 2, and 2k squared means 4k squared, 5 squared means 25. So k must be 13 times 4, that is 52, and then, or you can just cancel 4 and 2 to make it faster. So 4 and 2 will cancel. So you have 2 on top. So 13 times pi times 2 is 26 pi, k squared, then you have over 25. So note that in fraction, so this is equivalent to, it's like putting this up here, or you multiply or divide the fractions properly. So you have 25k over 26 pi k squared. And finally, just take away the k because you have k and over k squared. Take away 1k in the denominator, so you have 25 over 26 pi k. This is the rate at which the depth is changing with respect to k. So we were able to find what we want to find in this problem. Okay, so we're not aiming to get an exact number because it says in the problem that we just have to find the rate at which the height is changing in terms of k. So just to recap the solution, or to summarize, so the key in solving a problem in differentiation is knowing that whenever we speak of rate or rates, it's all about differentiation or derivatives. Again, if I say rate of change of the volume, it means dV over dt. If I say the rate of change of the depth, if it's in h, that means dH over dt. And always important that when you decide to differentiate an equation, you have to work on a single variable only. So that's the reason why we changed this k in terms of h, so that we can differentiate this in terms of h only. Now, just to recall, a while ago there's another option that why not change h in terms of k. If we have to do that, then you will be left with a k expression, and you will not be able to get dH over dt if there's no h there. That's why we simplify this and get the k in terms of h instead. And after that, so you just differentiate properly. So this is with respect to time. So change in v, or the derivative of v with respect to time is dv over dt, and then the rate of change in h is dH over dt. Okay, and then just continue simplifying until you get what you want to find. Okay, so that's it.